This is the second in a 2-video series looking at redox reactions in biochemistry. In the first video, we ask what is a redox reaction and how do cells use those redox reactions. In this video, we're going to say how do you calculate the energy of a redox reaction. So if you haven't checked out the first video, it might be worth it. Otherwise, let's just launch straight into this. So what we're going to be asking is what's the free energy change for a redox reaction? And this is actually a biological redox reaction that happens in the citric acid cycle. We take succinate and we react with this molecule ubiquinone, which I'm just going to call Q, and we form fumarate and QH2. And so what we're seeing is electrons are being transferred from succinate onto Q to make fumarate and QH2. A quick reminder, a redox reaction is just a reaction where we're transferring electrons from a donor to an acceptor. And we're going to be using the language that when this happens, the donor is being oxidized and the acceptor is being reduced. The fundamental equation we're going to be using to ask what's the energy of this is this one up here that says the standard state free energy for a reaction that involves redox is given by minus sign times N times F times delta epsilon. We'll get into each of those terms in a second, but to talk about the delta G naught prime part, this is how favorable is it to reduce the acceptor with electrons from the donor, assuming their concentrations are equal, right? This is all at standard state. The terms in this equation are N, which is how many electrons are transferred from the donor to the acceptor. F, which is the Faraday constant, so it's a constant. It's 96.485, etc., kilojoules per mole volt. And then this epsilon, this delta epsilon thing, which is the difference in the standard state reduction potential of the donor and the acceptor. Okay, so what we're going to do to unpack that equation, I should say here, don't worry, we're going to explain what a standard state reduction potential is in a second if that's not something that's just, oh yeah, I know what that is. But what we're going to do here is we're actually going to take a redox reaction and we're going to break it into two half reactions. And so I said that this is the reaction we're talking about, is succinate plus Q going to fumarate plus QH2. We can actually describe this as two half reactions, Q going to QH2 and succinate going to fumarate. And it's productive to think about those separately because we can actually think about the energy to take electrons from one to the other. So one half of this reaction, one half reaction, is a loss of electrons. And we can see that here. So this has, let's actually draw this. So we've got the hydrogens on here that aren't drawn in the picture. And then we've got hydrogens here. Now what we're going to do is I'm going to zoom in a little bit so we can do this. We're going to count the electrons that are in here, the pairs. So we got an electron pair here. 1, 2, 3, 4, 5. So we have 5 pairs of electrons distributed across these bonds. Another way to say it, we've got 5 bonds. We go over here and we say 1, 2, 3, 4, but we're missing some electrons. We're also missing some hydrogens, right? We had 1, 2 hydrogens on this side, on the product side, and we have 1, 2, 3, 4 hydrogens on this side. So what that means, to balance this reaction, we actually have to add on this side, we have to add 2 electrons that are floating off in space plus 2 protons, right? So we pull the electrons and the protons off, and we're just sticking off in space here. That is a half reaction, right? We haven't taken these electrons and protons and put them anywhere. We just pulled them off. So this is, we're losing electrons. What we'll see on the other side is the other half reaction is going to gain electrons. And so here we've got our Q and our QH2. Let's convince ourselves that that's true. So I'm just going to count now with numbers here. The bonds, actually, let's zoom back out. The difference between Q and QH2 is all in this ring structure, right? So we're going to count the bonds in that ring structure, and that will tell us about the electrons. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We count all the bonds there. If we go over here, we will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, we forgot. And then we've got bonds here between the oxygens and the hydrogens. So that's 12 and 13, right? So we have gone from 12 electron pairs on the left to 13 electron pairs on the right, which means to balance this reaction, we have to add 2 electrons over here. And we also, if you just go through and look at it, we gained 2 protons right here and here. So to balance the reaction, we have to do 2 plus 2H. Okay, so our previous half reaction, I'm going to actually go back to that slide. That previous half reaction, we had to add electrons and protons to the right side of the reaction because they're being lost from the reactants. On the other half of this reaction, we're actually having to put it on the left side. The electrons and the protons are the reactants that are going forward. And so what we're actually thinking about here is this transfer process. We're transferring from the succinate onto the Q as seen by these half reactions. Okay. So why do we break things into half reactions? Well, the strategy that we're going to use is we're going to calculate the energy to pull the electrons off of one molecule and then stick them back onto the other. That's what this equation, delta G equals minus NF delta epsilon, is going to do, is it's actually just doing this for us. Okay, how do we do that? Well, now we actually do need to talk about this thing called the standard state. Recall that I said that there's a difference in the standard state potential. That's what that delta epsilon thing is. And what that is measuring is the affinity of a molecule for electrons. And we can put it in a couple of different ways. So first, delta epsilon, the standard state reduction potential of a molecule, is measured in volts. The higher the voltage, the higher the electron affinity. So if something has more affinity, it will have a higher voltage. And second, I'm actually going to disappear. Another way to think about that is the higher the voltage, the bigger the difference in the arrangement of the electrons in the oxidized and reduced forms. Remember from our previous video, it's favorable to put electrons between molecules with higher electronegativity. This would be like, man, you're putting these in between atoms that have very high electronegativity. That would imply a high voltage, for example. Okay, so if we can describe the affinity of each molecule with a standard state reduction potential, we can start asking the question, and go back here, sorry. How much what's the voltage, the standard state reduction potential for doing this reaction? What is the affinity of this molecule for its electrons? What is the affinity of this molecule for its electrons? That is going to be measured by this standard state reduction potential. Okay, so you can look up standard state reduction potentials in tables. Biochemistry textbooks often have something like this. So here, this is from a standard biochemistry textbook. Here's a list of standard state reduction potentials. Too small to read, doesn't matter for the moment, but there are a lot of numbers in there. The way that these tend to be organized is actually, let's zoom up so we can look at it. They have some half reaction listed here. So this is a half reaction. We're taking molecular oxygen, we're adding protons, we're adding electrons, we're getting water, and then we're getting out, on the far side, this is the standard state reduction potential. Notice these are all written as reductions. So actually, here's one that we've already been looking at. Here's fumarate, going to protons plus electrons goes to succinate. That has a standard state reduction potential of 0.031 volts, right? So you can walk through a table like this. You can look up, these are the products, these are the reactants, or sorry, this is the, sorry, I should say that again correctly. You can look in one of these tables. What you're going to see is there is a reactant that is being reduced to give a product and a voltage associated with that. Okay, so you can look these up. When I said you can look these up in tables, you can also just Google them. I will put in one quick caveat. Danger there is to be very careful to use the delta G naught prime for a reaction because that is at pH 7. If you use a delta G naught, that's at pH 0. And if you have protons involved, which most of these reactions do, you will get radically different values. So make sure to get delta G naught primes, not delta G naughts. Okay. So we're taking electrons off of one atom, or one molecule, and we're sticking it onto another. We can describe those as two half reactions, and we can think about each molecule having an affinity for its electrons measured by a standard state reduction potential. Cool. So how do we actually do one of these calculations? So I'm going to go through it in 4 steps. The first is balance the half reactions to find the number of electrons that are being transferred. Identify the acceptor, which we'll see in a second, is the reaction you do not flip when you're balancing the equations. calculate the potential difference, so the standard state reduction potential difference between the atoms, and then you do some plugging and chugging. So let's dig into each of these. So first, balance the half reactions and find the number of electrons. So here's the reaction that I just showed earlier. We've got Q going to QH2 and fumarate going to succinate. These are the biological reactions we talked about. But when I drew the reaction, I actually drew it as this. I guess I should have put it up here earlier, or I should have shown the slide. But we've got succinate going to Q, going to fumarate plus QH2. That's the biological reaction that we're studying. And you'll notice that this is flipped here. Also notice that we've got this huge, all the electrons and protons are on the left and right. So what we're going to actually have to do to get this reaction to line up is we're going to have to flip this one over. So we flip that one over. And what that means is that we are going to be taking electrons from succinate and sticking them onto Q to make QH2. And we can see that by adding these two reactions together. So we're going to take this reaction and we're going to add it up with this reaction. That generates this. So we've got, I'm going to do it in boxes. It is officially behind me. Okay, we've got a box there. We get a box there. These are all coming from this top reaction. And then I'm actually going to switch colors. And then the bottom reaction here, we've got succinate coming in, and then we've got fumarate and the electrons here, right? So we've combined those reactions. We also now notice that the protons cancel, the electrons cancel, and we end up recovering our reaction, right? I had it up here at the top, but basically succinate plus Q goes to fumarate plus QH2, succinate plus Q goes to QH2 plus fumarate, right? So we've recovered our reaction with our half reactions. Now, we did this careful arrangement and balancing, but what we were able to identify with that is the number of electrons that are involved. And that number is here, 2, right? There are 2 electrons on the left, 2 electrons on the right. So our N for this reaction equals 2. We have 2 electrons that are involved. Okay, so that was step 1. Step 2 is going to be to identify the acceptor, which is the reaction we did not flip when balancing. So this right here was flipped. This was not. So this is our acceptor. Our electrons are going here. And this is our donor. Right? We didn't have to flip the acceptor. We did have to flip the donor. So now we've got our acceptor and our donor. Okay, so we balanced our reactions to find our N, which was 2. We just looked at that and said we flipped one of them over. That's our donor. Now we can calculate the potential difference. So if we look in a table at these 2 reactions, right? So that if we looked in the table, we would see that this one has a standard state reduction potential of 0.05 volts. This one has a potential of 0.031 volts. This is our acceptor on the top, right? We didn't have to flip that one over. This is our donor. Take the difference in those 2 values. So those 2 values here would be 0.045 minus 0.031. That is going to give us 0.014 volts. That is the potential difference between these 2 molecules. Okay, last step is we can just do some plugging and chugging, right? So here we've got our equation. This number was minus 2. We had 2 electrons that were involved in the transfer. This is Faraday's constant, which is 96.49 kilojoules per volt. And then this is our standard state reduction potential, which is 0.014, which if you plug in those numbers, you get minus 2.7 kilojoules per mole. So what this says, it is mildly favorable to oxidize succinate with Q. And indeed, that's how it's used biologically. This is a favorable-ish reaction that happens as part of the citric acid cycle. And once we get into metabolism proper, we're just going to see these over and over and over again. So this is a really helpful skill to have and to develop. Okay, I wanted to end with just 3 confusing points that I've seen over the years to just deal with. The first is that the higher the number, the higher the electron affinity. So most of biochemistry, most of chemistry, negative numbers are favorable, positive numbers are unfavorable. This is just totally backwards. So you just got to keep in mind, the higher the number, the higher the electron affinity. If it helps, you can think about it like a KD, right? A KD. Nope, the KDs are the opposite. Nope, totally lied. Don't think about it like a KD. The higher the number, the higher the electron affinity. Redox is just an exception. So oxygen here, high electron affinity, acetate, low electron affinity. All of redox flow in sort of human biochemistry basically consists of flowing this direction. That's favorable. This is how we get energy out. So high number, higher affinity. A second confusing point is there's this weird 0 point in the middle, right? We're like, well, what is a standard state reduction potential of 0 versus minus 7 and 0.8? Like, why is there a 0 point? And it turns out, in terms of doing the calculations, at least, that it's completely arbitrary. There are some real reasons that we have it that way, but they don't matter for the calculation. This is actually just like what we would do with, say, oceans. So we would say, oh, look, there is the water level. That's 0. When we talk about elevation, we might say, oh, this is plus 1,000 feet. And then we talk about depth, we might say, oh, that's minus 1,000 feet. But if I wanted to say, what is the distance between those two, I would say it is just 2,000 feet, right? So don't worry about the sign on your standard state reduction potential, other than you need it to sort of say whether you're in the ocean or you're in the mountain, and that gets you the difference between them, right? But the sign of a minus 7 doesn't really say anything different than a plus 7, other than it's saying this one, because it's higher, has a higher affinity than this one down here. Last point of these that I found confusing is I've just found over the years that it's, like in a lot of calculations, like, well, what should I do with my standard state reduction potential? If I flip, one of the big things that I see is a student wants to flip their flip their acceptor standard state reduction potential, and they want to change the sign on their standard state reduction potential. But good rule to keep in mind is never alter this in any way. Don't flip its sign. Don't multiply it by anything. When you're talking about a standard state reduction potential, you're really asking about, going back to my picture here, how far am I moving along some distance axis, some elevation axis? Just take the numbers for what they are, take the difference between them. Don't ever change your standard state reduction potential in any way. Okay, only do this. Just take the difference between the two. So again, here are the quick steps of this. When you're faced with a redox reaction, you want to take the half reactions that make that up, balance those half reactions to figure out how many electrons are involved, the N, identify the acceptor, take the potential difference between those two, and then plug and chug. And you're going to be plugging and chugging with this equation, delta G naught prime equals minus N times F times the acceptor minus that of your donor. And if you plug those numbers in, you can always get the right answer for the standard state reduction potential of a redox reaction that we'll encounter across metabolism. Okay, so that is what I have. This is this 2-video block on redox chemistry. Hopefully it was helpful. I look forward to seeing you later.